Welcome to Oxford Earth Sciences. My name is Chris Ballantyne. I'm the Oxford Professor of Geochemistry and Head of Department. Earth Sciences today has never been more relevant, whether that's understanding the impact of climate change, protecting us from natural hazards such as volcanoes, earthquakes and tsunami, or developing techniques to explore for new resources essential for a successful future society, and also responsibly managing disposal of society's waste within the geological context. For me, it's not just these really great applications of earth sciences, but also just the simple intellectual curiosity about how our Earth formed and evolved. How did it develop to what we see around us today? From planet formation, the origin of the atmosphere and oceans, to the initiation of plate tectonics and the evolution of life, the tenacity of life, and also the way in which life has interacted with and shaped the entire planetary system from the surface right the way through to the planetary interior. To understand all of these, we truly draw upon all of the sciences and integrate across those, from physics to chemistry to biology, within a quantitative sense using maths. Whatever you plan for your future, the ability to bring together complex data and quantitatively make sense of it using the different sciences is a skill set second to none and transferable to almost all disciplines and area of career. I invite you to join me and my colleagues and learn more about Oxford Earth Sciences through the material that we've put here today. Enjoy.
My name's Conal McNichol and I'm here to tell you about the Earth Sciences course at the University of Oxford. The Earth Sciences department at Oxford teaches at both undergraduate and graduate level, and our aim is to conduct excellent research and excellent teaching in our course. And we're a relatively small department. We have about 30 full-time faculty, 50 or so research fellows or postdoctoral research associates. And these are research scientists who are often world leaders in their own respective fields. We have about 80 postgraduate students at any one time doing research in a wide variety of topics, and of the order of 130 undergraduate students. So we're a scientific community of about 300 people. So what are the earth sciences? Well, the take that we have on them in our department is that it involves the application of the basic physical sciences to the understanding of our planet. And so what we do is we take basic chemistry, physics, maths, and biology, and we apply that to understanding how the Earth works today, how it may have worked in the past, and use it to project how the Earth might work in the future. What's the relevance of doing this? Well, for a typical applicant in 2020, they would have been born in the early part of the 21st century. When I was born, I was one of only 3.5 billion on the Earth. Whereas an applicant today would have been almost the 6.5 billionth person on the surface of the planet. And if we come to 2020, we find that we have a global population of around 7.6 billion. And there are a number of challenges associated with that. The three grand challenges that face society, particularly with those increased numbers, is how you feed a global population of that size, how you protect that global population, and so that's things like natural hazards, how do you keep people warm, how do you make sure people are clothed, and the third grand challenge is that those first two challenges, the number of people on the planet, how we keep them fed and how we keep them safe, involves the consumption of natural resources. And the consumption of natural resources comes with its own particular set of problems associated with them. Problems of pollution, as illustrated in this stream on the top, and problems of climate change, as illustrated by these melting ice flows in the bottom diagram. And the earth sciences are central to addressing all of these challenges. The research we do is of scientific relevance, but it's also of societal and even commercial relevance. So as an example, modern day medicine and things like MRI scanners depend heavily on natural resources of things such as helium to keep those superconducting sensors cool. And our department has been at the center of efforts to try and find reservoirs of helium on Earth that can be used to alleviate shortages in these important materials. So how do we study the planet? Well, as I've said, we focus on the application of basic sciences, biology, chemistry, physics, and maths and geology, towards trying to understand how the Earth works. And we have a very quantitative focus and a very quantitative approach in our department. And that approach requires that we integrate theory, observations that we can make in the field, so we go and do fieldwork, or in the lab, or the observations we make in experiments or in computer models towards trying to understand the Earth. We also have to work on a range of timescales. So the trace on the bottom is a seismic trace. It's the shock wave from an earthquake that took place on Boxing Day in 2004, and the trace is essentially recording the first 90 minutes of the shock waves arriving at a particular location distant from the earthquake. And so these are geological events that last for seconds to minutes, but of course we have to look at them across the entire span of time, which is depicted in this particular diagram, where the first humans appear very close to midnight if we were to view this as a clock, but we have to go all the way back in time, back to about 4.5 billion years for the entire history of the Earth. So we deal with a vast range of timescales, and we deal with a vast range of spatial scales. There are some processes, things like ocean circulation, that have to be modelled on the scale of a planet, but we also have to measure things that are happening right down at near nanometer scales. And in this case, we're looking at the magnetization of a set of materials here. And of course, we also have to think about processes and things that happen on the Earth in 3 dimensions. So we have a depth scale to consider as well as a surface scale. So of the basic sciences, probably physics is really the only other field that actually deals with that range of spatial and temporal scales. Now, the science we do essentially covers everything from the deep Earth in here, right the way through what lies beneath the crust, so in the Earth's mantle, and right the way out to the surface in the form of the crust or the lithosphere. And we're also interested in processes that take place in the layers above the surface. So we're interested in the atmosphere, in the hydrosphere, which is the oceans, the biosphere, and of course the cryosphere. The cryosphere being ice sheets and glaciers. And of course, to understand the Earth as one planet, it's important that we look at other planets. So we also do research covering things like the Moon and other planets within the solar system. So we have comparators. And we use that to address some very, very fundamental questions, such as how do planets form, why planets, different planets have followed different evolutionary paths. So there's Mars, for example. Other kinds of fundamental questions we're interested in is how did life originate and evolve on Earth? So here are the remnants of some very, very old algal mats. Here's an element of modern day life. These are deep sea vents, so-called black smokers, and one of the major discoveries of recent decades has been the number of life forms that thrive in these sorts of settings and derive their energy from what we call chemosynthetic processes rather than the photosynthetic processes that dominate at the Earth's surface. And of course, we're not only interested in looking backwards, we're also interested in looking to the future. And one of the major areas of research that we and other Earth Sciences departments have is how the planet will react to rising CO2 levels. So this particular diagram is showing the CO2 concentrations at an observatory in Mauna Loa in Hawaii. And this one is a famous one. It's called the Keeling curve because they've been taking continual measurements there for the last nearly 7 decades now. And they've been able to document the changes in CO2 over time, and in particular the rise in CO2 over time. So we know that CO2 in the atmosphere is rising, and we're interested in what does that mean for other aspects of our planet. So, for example, is that likely to lead to a greater frequency of hurricanes in certain parts of the world? Is it likely to lead to rises in sea level? And what does that mean for coastal communities? And the other thing that the earth sciences, of course, brings to all of this is the long-term perspective. The long-term perspective of how the climate has evolved through time. So the diagram on the left-hand side is a satellite imagery of the British Isles, and you can see these white patches, or the pale blue patches down here. These are massive algal blooms. These algal blooms, which cover many hundreds of kilometers in this particular satellite image, are actually formed of billions of these little things. These are micron-scale, single-cell phytoplankton known as coccoliths. And these coccoliths have these external, we call them tests. Their external form are made of little discs of calcium carbonate, and these little discs are the things that actually give us a record of past climate. Because they have to make these discs from materials that are present in the seawater at the time, and of course when they die, the soft parts rot, but the hard parts settle down to the bottom of the ocean, and eventually when they get compacted they form things like the chalk cliffs of the south coast of England. And so I've showed you earlier on a 1-year record of CO2 in the atmosphere. This is a much longer term record. This is one that includes the data from the Mauna Loa Observatory after 1958, but it also includes records from ice cores that go back almost 800,000 years. And on the longer term record, we can see the waxing and waning of ice ages in this record. And so where CO2 levels are low, we had ice ages, and then where CO2 levels are higher, we are in interglacial periods. And you can see that the CO2 levels that we see for the last 800,000 years are typically somewhere between 170 and about 250 or 260. Whereas the modern day levels, and the right-hand side of this is actually real data, it's not an axis of the graph. This shows the massive increase in CO2 since the Industrial Revolution. The current levels, as we've said, are now heading up for 420 parts per million. Now, those changes in CO2 levels, as we've said, for the last 800,000 years, have marched in step with the waxing and waning of global ice sheets. And we can see that, as I said, the CO2 levels that we observed in the recent past, at least, are nowhere near the current day levels. And so one of the major areas of research in the earth sciences is trying to understand what that massive increase in CO2, which is predominantly due to anthropogenic or man-made influences, the combustion of fossil fuels in particular, what effects that's likely to have on climate. We can go back even farther. So instead of just looking at the tiny bubbles of air that are trapped in ice cores in the previous one, and this diagram has flipped the axis from the ones you saw before, but we can actually use the records that we get in foraminifera and in those tiny little coccoliths to actually go back even farther in time. And we can see what Earth's climate was like on timescales that go back beyond the last few 100,000 years, and we can go back millions and millions of years. We're also interested in natural hazards. So here we have an example from a 1999 earthquake in Turkey, the Izmit earthquake, where you can see that the ground, the top of the photograph, moved to the right relative to the ground at the bottom of the photograph, and that was due to an earthquake on a major fault that goes through here. Now, our ability to understand and map these hazards has been massively improved in recent decades by the advent of high-precision satellite measurements. We've also applied it in a whole range of other settings. So there was a major earthquake in Nepal in 2015, and members of our department at the time, and this was the aftermath in the main square, and scientists in our department have been able to map out those ground displacements and note where the major ground motions were. Now, our interest in Nepal hasn't been primarily scientific. We've also had a very practical impact in in Nepal, because Mike Searle, who you can see here, has spent many decades working in Nepal and mapping the geological structures in Nepal. And he was heavily involved in a fundraising initiative that rebuilt a primary school in one of the areas where he's done a lot of work over the years in the Gorkha district. And so the department and friends of the department helped fund the rebuilding of a new primary school. Turning to our course then, what the purpose of our course is to try and give everybody who takes the course the tools, effective tools for investigating the processes that govern the evolution and present-day state of our planet. So in particular, we're going to be interested in using those basic physical sciences to try and develop insights. So the purpose of our course is essentially twofold. One, of course, is the vocational one. We want to train you for future careers. We want you to be able to get a job after doing our degree. But another aspect of our course is brain stretch. We want to give a course that's intellectually stimulating and challenging, and that will push you beyond what you already know in a wide variety of fields and challenge you to really engage with some deep and profound problems. And so our course is structured in the first 2 years to give you a sound basis across a broad part of the earth sciences. And so everybody will take courses in physics, chemistry, biology, and maths, as well as courses in geology and syntheses courses that try and put all these things together. We continue that in the second year, but once you reach the end of the second year, then we permit a high level of specialization. And so you can choose advanced options that are close to your own particular interests. So if your interests are more towards geophysics or natural hazards, you can plot a path through the course that emphasizes those particular areas. And one important part of our course is the fieldwork, because we feel that observing earth processes and documenting earth processes in their natural settings is a key part of understanding how the earth works. And so there are field courses in every year of our course. At the moment they cover localities in Wales, Scotland, in southern Britain, in Spain, in Greece and in Bermuda. These may change in the future, but the goal behind them will always be the same. The goal will be to use observations and document things we can see in the field in order to understand earth processes. There are 3 components of independent work involved in the undergraduate course. All our second years undertake what we call a mapping project, where they go and document the geology of a particular region of their choosing, and recent projects have extended as far afield as Greenland, New Zealand, Canada, as well as in the UK and in Europe. Our third year also has an extended essay, which is a review paper of a subject of your choosing, and half of our fourth year is given over to a research project. And the point behind the research project is it's not a Mickey Mouse thing designed to keep you occupied for 6 months. It's a real research project embedded within a research group within the department, and a significant fraction of these end up as publishable papers. They end up being published as manuscripts in the scientific literature. Typical week for our undergraduates looks something like this. This is taken straight from our first year timetable, but you would expect to have somewhere between 8 to 10 lectures, normally in the mornings, and then in the afternoon, depending on the particular week, you might have 3 or 4 practical sessions where you apply some of the skills that we try and develop through the lecture course to real settings. When trying to choose which college to apply to, and I mentioned at the beginning that Oxford is a collegiate university, so all students are members of both colleges and the department or the university. There are 7 colleges that currently accept earth sciences students. These are Exeter, St Anne's, St Edmund Hall, St Hugh's, St Peter's, University College and Worcester College. We coordinate admissions within our department centrally, and so the idea behind that is that it doesn't matter which of these colleges you put down as your choice. Your chances of being offered a place on the course are the same, no matter which college you put down. All students receive 2 interviews. These are given by 4 tutors representing 4 different colleges. And we centrally decide which students we want to take onto the course, and we then respect their choice where possible as to which college they go to. In terms of admissions, we require that you've taken A-level maths or equivalent and either physics or chemistry. But we don't mind what your 3rd or indeed 4th A-levels are. Recommended ones would be physics, chemistry, biology, further maths, geology or geography. And our typical offer is A-star AA if you're taking 3 A-levels or 4 A's if you're taking 4. The earth sciences are unique amongst the physical sciences, at least in that we have a roughly even male to female intake. And finally, the range of careers that you can go into from the earth sciences is vast, and this is something that was developed by the University Careers Service. But in essence, we break these down into 3 different groups. We break them down into what we call vocational career choices. So these are ones where you'll be applying geology directly in your everyday work. And so these could include energy and renewables, environmental, water, engineering, geology, etc. And about 1/3 of our students go into those sorts of fields. About 1/3 go into what we call non-vocational careers. So these are ones where you're not applying your skills, geological skills, directly in your everyday job, but they may still have some relevance. So that would be things like policy and administration, science communication and publishing, education, etc. And about 1/3 will go on to further study, and about 1/3 will go on to take further degrees, possibly look at research careers. Finally, if you have any questions, you can contact the Earth Science tutor at the college of your choice. All their details will be online on the departmental website, which is www.earth.ox.ac.uk, and we're happy to accept inquiries and queries at inquiries@earth.ox.ac.uk.